So we're moving into Chapter 5. The title of the chapter is Transient Conduction. We're not done with conduction yet. We haven't moved our focus over to convection and radiation. We're going to do that soon, but we're still in conduction, and we have transient conduction. So we had the heat diffusion equation. Can you recall the heat diffusion equation? Something like, I don't know, del squared T plus, you can put the K there, Q dot equal to rho C rate of change of T with respect to time. So this was our diffusion heat conduction part, the Laplacian of temperature. This was if you had any heat generation, volumetric heat source. And this term, so far, we've been ignoring, but now we're not going to ignore it, are we? It's the transient part. It's where the temperature is a function of time, as well as possibly space, location as well. Well, when we first start into it, it seems very funny that we're going to have transient conduction, but we're going to neglect the conduction. And it'll be a lump capacitance. And so the boundary condition is convection, and there's no real conduction resistance. It's neglected within the system. So that's the first two parts. There's a generalization of the lumped capacitance analysis. These two sections, I'll mention it again, are very important. This one you can skim. We just don't have time to plow that deep, okay? But it's not until section 5.4 and beyond that you really get to the temperature is a function of time as well as location inside a material that's undergoing transient conduction. All right, we will get this far today, hopefully. Lumped capacitance method. Well, it's an approach to solving a problem. The way I like to set it up is start with an object that is initially hot, and it has a temperature Ti. And we're interested in tracking that temperature of that object starting at time 0 when it has initial temperature Ti, as it's dunked or abruptly moved from a zone where it was uniform temperature Ti out of that zone, maybe dunked into a fluid or moved out of a furnace, and now it's exposed to some other fluid at a lot different temperatures. So here's a bucket. It's filled with the fluid, large fluid bucket, and that temperature is T infinity. And when that object becomes dunked into that fluid, there's a convection to cool that object. Think of the fluid as being lower temperature, T infinity being lower. It works if you take a cold object and put it in a hot fluid as well. But mathematically, I think or conceptually, it's easier to start with hot object. So this is our object, and we dunk it into a fluid. And what happens to the temperature of that object as a function of time? Well, it starts out at that T initial, doesn't it? And what does it do? It's going to go to eventually the fluid temperature, T infinity. So it's eventually going to get to that temperature. What does it do? Does it go like this? No. It's not going to be a linear temperature profile as a function of time, is it? Is it going to be something like this? That's dynamics. You have to have inertia in the system. And what we have in thermal systems, thankfully, nothing with the second time derivative. It's always just the first time derivative. So there's no thermal inertia. It's a lot simpler than dynamic systems. And so what does it do? First order system. How do you describe that function? It's not sinusoidal. It's not hyperbolic. It's just a simple old exponential. The one we like. It's easy. So let's set up the math to solve for what we anticipate being an exponential temperature as a function of time. All right, so you start with the first law, which is basically an energy balance. So the energy balance says the rate of change of energy inside the system. What's our system? This little object. The rate of change of energy inside that system as a function of time can be expressed as the negative of Q going out via convection. I know that it's out by convection, so I'm going to represent a rate of heat transfer, positive convection, and make that minus sign apparent right in that equation. Okay. So how is the energy stored in the system? The mass, specific heat, the temperature. So when I take the time derivative, the mass of the object doesn't change, the specific heat doesn't change, it's just the temperature that changes. So we get that the mc dt d time is equal to minus, and our model for convection, HA T minus T infinity. So here's the same temperature there and there. That's the temperature of the object. The rate at which it's convectively cooled is greater when the delta T between the object and the fluid. So if you come over here, what about the slope right here? It's the highest because the delta T is the highest, and the slope goes down because the rate of cooling is lower because the delta T driving the convection is lower. All right, so I think we can manipulate this equation a little bit. dt d time equal to minus HA d, mc, or you could put rho v c, right? What's rho v c? Well, rho v is the volume times the density, that's the mass of the object. And then you have T minus T infinity. You could introduce, like the textbook, a temperature difference, theta. That's just T minus T infinity. You can plot theta as a function of time. What does theta do? It starts off at theta initial. What does it go to after a long time? The temperature difference theta goes to 0. And so it's the same shape and everything else, but it's a little simpler. So what do we have for our differential equation? d theta dt is equal to minus HA over rho CV theta. With the initial condition, theta initial, theta at time 0 is equal to theta initial, which is the initial temperature minus the temperature of the fluid. So let's solve this problem. Separate, integrate. We get 1 over theta d theta equal to minus HA over rho CV times dt. When we integrate, all those terms go outside the integral. We integrate 1 over theta. We go from the lower limit, theta initial, to any future theta, time initial 0 to some future time t, and you incorporate the boundary conditions that way. The natural log of theta over theta initial equal to minus HA over rho CV times t. At this point, you can even say, if I'm interested in calculating the time required for an object to cool from some initial temperature theta initial to some final temperature theta, I can just use this equation right here, and I use that minus sign to switch theta initial over theta. Okay, you'll get rho CV divided by HA. That's one useful expression. Somebody says, I take this object, I change its environment, and the lumped capacitance model is valid, and I'm just looking at temperature as a function of time. How long does it take for the temperature to change from this initial value to that final value? And then what you do also is express the final answer for theta is equal to theta initial e, the exponential, of minus HAT divided by rho CV. There's the other equation. They're both the same equation, aren't they? It's just, are you interested in finding the time that it took to cool it, or are you interested in the temperature after this much time? All right. So there's our equation. Theta over theta initial, or T minus T infinity over Ti minus T infinity, equal to the exponential minus HA over rho C V and then T. So right away, we look for analogies. We look for things that you've already studied and mastered before. How many people remember that you studied a capacitor that's charged? Maybe you set it up like this. You have a battery. There's my rendition of a battery. A switch, a capacitor, and a resistor. So initially, the switch is closed, so the battery can send electric current over to that side. And what happens is after a while, initially, it really starts flowing through the capacitor a lot. But after a while, the capacitor builds up voltage. There's a big voltage across the capacitor. And what happens is the current no longer goes through the capacitor to charge it anymore. It just goes only through the resistor. True? That's all to get the system set up. But then what do is you open up and disconnect the battery from the system. What happens to the system now? The capacitor was charged, fully charged. It's like a hot object. Now it's just dunked into a cold fluid tank. What happens to the voltage across the capacitor? It's going to discharge. And the flow of current then is going to go in this loop to discharge it. Where is it going to go? Through the resistor. And you study that. It's a first order system, and you get something where you have a decay, exponential decay of the voltage across the capacitor. True? All right. So we've been exposed to things that have this exponential function, exp, and sometimes you even write it as minus t over tau, where tau is a time constant, but in this case, it's a thermal time constant. Just doing some name calling, what is the thermal time constant for this problem, tau? Rho CV divided by HA, isn't it? Isn't that the thermal time constant? Okay. And then you become familiar. Anybody recall the time constant in a RC circuit? I think it's RC. All right. Let's do this. So let's go back and review this a little bit. You have the theta over theta initial. What does that start at? What does that start at? Doesn't it start at 100%? And what does it go to? 0. True? That's our exponential shape. All right. Then there's a few things that we want to master about this exponential function. If you have your calculator, you can use it to remind yourself of a few basic facts, right? But if I evaluate the slope of the line right here, and I project the slope of that line down to right there, this is the time axis, t. What is the value at that location? It's the time constant. All right, there's another fact. I say I have, because this is what we're playing with. We're playing with, let me get this out of the way. Maybe it's not so obvious. Get this out of the way. Whoops. Get this out of, okay, get it out of the way. There you go. It's equal to theta over theta initial. I'm looking at this equation right here. It's a simple exponential, isn't it? Okay. If I go out tau, that's how much time I go out. That's the time constant. And I come up and I evaluate the function right there. What is the value? It's between 0 and 1. What is e? The question is, what is e to the minus 1? Anybody without going to their calculator can remember that? What is e to the minus 1? 1 over e. Oh, cool, yeah. But what is it numerically? Your life depended on it. It's just rough. Give me a number. around 0.4, around 0.37, 0.37. Roughly a third. 2/3 of the action is gone. All right? Or 60% or 63% of the action is gone. 37% is still to happen. Okay? So this is about 0.37, roughly a third. All right. Now, somebody says go out 3 taus. How much of the action has already occurred? How much is still left to occur? You go out 3 time constants, e to the minus 3 is equal to 0.05. 5% is left, 95% has happened. You have a calculator? Check it. And then you say, how long do I have to go before this exponential actually gets all the way to 0? Infinity. You're not going to be able to wait that long. How close is close enough to really call it close enough to 0? Less than 1%. If you go out 5 time constants, what is the value e to the minus 5? Less than 1%. About 0.7%. 0.7%. You very rarely find somebody that says, I need to wait more than 5 time constants for a system to get to 0. It's like, it's there. A lot of engineering applications, it's like 5%, you're there. Okay? Because there's noise and other uncertainties in the system. All right, let's go over here and ask some questions. First clicker question. What are the units of the thermal time constant? Seconds, inverse seconds, degrees C per second, second per degree C, or dimensionless? Dimensionless. And as a reminder, this is the symbol, tau. It's rho VC divided by HA. You got 5 seconds. All right, we're up. I'm closing it down. All right, let's go back and take a look. Weren't we just plotting theta over theta initial? What was theta? The units of theta? Degree C. Theta over theta initial. What's the units on theta over theta initial? Dimensionless. All right. Is equal to e to the minus t over tau. Mathematically, somebody says, I'm running some calcs and I calculated this number x, and I divide it by, I don't know, b. And x has the units of meter, and b is -2 without any units or anything. And I want to exponentiate x over b. So I want to evaluate e, 1, this is 1 meter, so -1/2 meter. Good idea or bad idea? Why is that a bad idea? Can I take and exponentiate anything that is not dimensionless? Can I exponentiate something that is, I don't know, degree C or Kelvin per meter or whatever? I mean, when you take and exponentiate something, this must be dimensionless. So I take a look. T, what are the units on T? Seconds. What has to be the units on tau? It's a time constant. It's kind of given in the name, isn't it? So we ready to grade it? This shows me that you guessed as a class. Now, there's a small, hint that A is the correct answer, so I like that. But when we come back over here, there are probably a whole bunch of people yawning. Oh boy, I'm bored. Thermo and heat transfer first order systems. I can't wait to get to some more exciting, vibrations where we overshoot and undershoot and damp and all that. This whole class is just first order systems. Well, own it. It's like, yeah, this is your old friend, but make sure it's your old intimate friend. All right, so let's go on. Let's ask another clicker question. The initial temperature difference is 50. You don't need a calculator, but it's better if you use one. But you can use your brain and figure this one out. The initial temperature difference is 50 degrees C. The time constant's 20 seconds. So if you want to put, you say theta I is 50 degrees C. Tau is 20 seconds. What is the temperature difference after a time of 20 seconds? What is the temperature difference? Everybody in? So let's stop. And we show the results. And why is 18 degrees C the correct answer? Because it's 37% of 50. Let's say I can't do 37% of 50. Do 40%. 0.4 times 50 comes in at 20. So I'm a little bit less than 20. So it's 18 and a half or so, right? Makes sense? Not trying to be tricky. But what did we just exploit? That fact right there, that's equal to 0.37. You ready for the next clicker question? Not really, huh? The initial temperature difference is the same as the previous problem. The initial temperature difference, theta I, is 50 degrees C. The time constant's the same, 20 seconds. What is the temperature difference after what's theta at a time of 60 seconds? All right, let's go ahead and stop it. And what did we just use? E to the minus 3. 0.05 times 50, 2.5 degrees. The action's pretty well over. You went from 50 degree delta T down to 2.5. I know there's still some action left, but there you go. Well, you said you're going to neglect the conduction or the temperature difference in the solid object. The temperature in that solid object, no matter if you're in the middle or toward the edge or right on the edge, that temperature is all the same in the lumped capacitance method. So, well, what is that assuming, or how do you justify that? Well, what you do is you think of maybe a temperature in a slab that's convectively cooled. Let's say the temperature starts uniform, very hot. We subject it to a cool fluid. The fluid is way down here in temperature, and you get a dramatic temperature drop like that. And over time, the temperature has a little bow in it, of course, just a little bit, but the preponderance or the majority of the temperature difference between the object temperature and the fluid temperature is just in the boundary layer, in the convection resistance. And so it continues to cool like that. Versus this opposite, if I have an object like this, and it starts at the uniform temperature, it's exposed to the fluid out here, and it has a hard time conducting the heat from the interior to the edge so that it can be convected off, you may get something that looks like this inside, and then like that. And then it continued like this, right? That is not justifying lumped capacitance. Don't use lumped capacitance in the case on the right. You use it on the left. So how do you justify it? You say, well, somehow the resistance to heat transfer, that's conduction within the object, the solid object, is really small compared to the resistance of convection heat transfer from the surface into the fluid. Well, what's our generic equation for resistance conduction? L over Ka. What's our generic equation for resistance convection? 1 over HA. You kind of put them together and you throw this on the other side and you'll say that HL divided by K needs to be much, much less than 1. That's the criteria. If that's valid, lumped capacitance is justified. So that's our test. So two things. Biot number is defined as this HL over K. So there was a person, last name Biot, did a lot of work. They honored him by attaching his name to this equation. That's the Biot number. Let me ask you a question. Is it kind of like the Reynolds number? A little bit, because Reynolds number, what are the SI units associated with the Reynolds number? Dimensionless. What are the SI units associated with the Biot number? Watts per meter squared, degrees C, watts per Kelvin, what? It's dimensionless, unitless, that's right. Okay, and so you have that the Biot number needs to be much, much less than 1, and that justifies the use of the lumped capacitance. Next question is, what is much, much less than 1? What is much, much less than 1? That's an engineering judgment call. So the engineering judgment is that the Biot number of less than or equal to, I've seen a tenth, I've seen a sixth, somewhere in that vicinity. If you start getting larger than that, let's say the Biot number you calculate and it's 0.2, don't do it unless you really like a large error or can stomach or handle a large error, right? But a lot of times you'll calculate the Biot number and it'll be 0.003. Guess what? That's pretty small. Let's use the lumped capacitance method. Did you have a question?
You did clear that up, but I did want to point out maybe that that's a corrected length.
Okay, that's the next slide. All right. So that's a tenth, 0.1. This is either or that. So 0.1 or 0.16, somewhere in there. Different books have a different criteria for cutoff. That's what I mean. Is so if the Biot number is less than or equal to 0.1, use it. 0.1 is much less than 1, but it's an engineering judgment call, what that means. This one is a little harder to interpret. This one's a little easier to interpret. But when the number comes in like this, which it often does on a lot of problems, you don't have to worry how close am I to the cutoff. What's the cutoff to justify it? All right. So now let's think about a slab coming out of a furnace. Think of a big piece of metal and it's coming out, and now it's subjected to air. And it's subjected to air on both sides, and it's being cooled on both sides. Well, if you introduce the slab thickness 2L, hence the half thickness is L. Okay? So what do we have is we have the characteristic length we're trying to develop, L sub C. We go back and we say, well, what was the, if you just look on a side scale right here, the heat that's the warmth of the object, the high internal energy that's going to be decreasing, reflected by a decrease in the temperature, that's got to make it to the surface and then off the surface into the fluid, true? Well, what's the furthest path that any little pack of heat would have to traverse to get out of the system? Well, right around here, a little bit to the left of the center line would have to flow out. If it's a little bit to the left, it goes that way. If it's a little bit to the right, it goes that way, right? So you say to yourself, what would be that resistance? That's the half thickness divided by K area. And then you could think of it, just half of it or double it, and you have two sides for convection. So that's the conduction resistance, and the convection resistance is equal to 1 over HA. Put them together. We just did this. We get LA HLA divided by KA. Well, I canceled the A's right away. But what is L times A? It's a volume. Divide that by an area, and now that's our equation that we can use for a more general problem other than just slabs for cylinders and spheres. So the characteristic length is the volume to area ratio. We generalize this concept. It works out to be the half thickness for the slab. Let's take a look at a long cylinder. So what is the volume for a long cylinder? Is it pi r squared times L? This is the L. And r is the radius. Thumbs up if you agree. What's the area for the convection off of the cylinder into the fluid? Is it 2 pi RL? So what is the characteristic length as the volume to area ratio? It's pi r squared L divided by 2 pi RL. Let's cancel the L's. Cancel one of the R's, cancel the pi's. And the characteristic length is the radius of the cylinder divided by 2. Half of the radius. Let's do it for a sphere. So we have the sphere. And we say, what's the volume? Oh, this is the hard part. 4/3 pi r cubed. What is the surface area? 4 pi r squared. The characteristic length, the volume to area ratio, comes in 4/3 pi r cubed, 4 pi r squared. The r squareds cancel. You get the pi's cancel, the 4 cancel. The characteristic length for a sphere is the radius divided by 3. So it's easy to kind of remember. For the slab, the characteristic length is the half thickness. Let me just write it out, half thickness, which is just L a lot of times, because we use 2L as the thickness. And for a cylinder, it's radius divided by 2, and for a sphere, radius divided by 3. Well, the Biot number we just introduced. And when you get to chapter 6, there's a table of properties that are dimensionless ratios. And so the Biot number, defined as HL over K, is interpreted as the ratio of internal thermal resistance in the solid to the boundary layer or convective thermal resistance. Does that make sense? I know this is in lingo of chapter 6, but that's what we have. There's another parameter. It's the Fourier number. The Fourier number is defined as alpha t divided by L squared. All right. First of all, what is alpha? It's K over rho C. Do you recall seeing alpha? I think it's in chapter 1. What is the name of alpha? Thermal diffusivity. Thermal diffusivity. It's just another property of a material. Does copper have a thermal diffusivity? Yes, just like it has a density and just like it has a thermal conductivity. Does air have a thermal diffusivity? Yes, just like it has a density and a specific heat and other properties, conductivity, etc. So this is just a convenient grouping of terms, K over rho C. All right. The Fourier number is, as it's shown, alpha T over L squared. It's the ratio of the heat conduction rate to the rate of thermal energy storage in a solid. Basically, it's a dimensionless thermal time. That's what it is, a dimensionless thermal time. So if the Fourier number is low, it didn't have enough physical time to transfer a lot of the heat. The Fourier number is high, there was a sufficient thermal time for transferring a lot of heat. All right. Well, where would you see this? Well, if we go back to this equation, theta over theta initial equal to e to the minus, what were our equations again? We have the h we had the temperature, we had, oh boy, we had the rho, C, V, and K. Did I get them all right? No, I don't have the K. Rho, C, V, H, T. That was it. True? I needed the area. That's what I needed. The area. There you go. And then this is the time. Well, do this. Put that area down here. And what do we call the volume to area ratio? It's like a length. It's like a characteristic length for a slab, half thickness. Okay. Take this equation and multiply by volume to area over volume to area. We didn't change anything, did we? And then multiply by thermal conductivity over thermal conductivity. We didn't change anything. And what we can find is that you'll grab out the H L over K. What was that known as? Biot number. Multiply by the temperature. K over rho C is alpha, L squared, Fourier number. So I know it gets pretty abstract, but you get the dimensionless temperature difference ratio equal to e to the minus Biot number times Fourier number. You'll see increasingly the use of these dimensionless parameters, especially when we get to convection. All right. Well, these two sections are very important. You need to be able to use the lumped capacitance method. You also need to be able to justify its use. This is nice, but basically the idea of lumped capacitance is what? What's the key idea in lumped capacitance? Neglect the internal resistance, conductive resistance within the object. What happens is you could have an object where on the boundary of the object I have thermal radiation in addition to or just by itself. And you can have a lumped capacitance model with radiation only or radiation with, I think this one is where they have variable temperature dependent coefficient for the convection, or they have with heat generation within the solid and other considerations. Well, they're all neat and they're all applicable. We just don't have time. So skim it, skip it, either way. All right, but what's the key idea? Let's ask another clicker question. What is the main assumption underlying lumped capacitance method? Is it A, the temperature is constant in the solid object? B, the temperature is uniform in the solid object? C, the temperature is a function of location in the solid object? Or D, temperature is a function of time and location in the solid object? Or that the Biot number times the Fourier number is much, much less than 1? All right, we got to shut it down. So I tried to say it, I don't know how many times so far this lecture, right? We'll see what the percentage is. Oh, come on. Come on now. Am I trying to hide this from you? What's the key idea? If the resistance of the conduction within the object is negligible, then the temperature within the object is uniform. It's the same temperature throughout the object. Oh, the object temperature can change with time. It can go up or down, but there's negligible temperature difference as I move around from the interior of the object to the surface of the object. The big temperature difference is between the surface and the fluid. It's not that it's constant. What does A imply? What does A imply? If it says, oh, it's constant, steady state, it's not changing with time. That's not true. If it's uniform, where did we see the uniform? We used this Q dot. Typically, it's uniform volumetric heat generation. Uniform meaning everywhere throughout has the same. So that's the right term, isn't it? Isn't the temperature uniform? So 40% of the class got it. We're going to work harder to get the other 60% on board somehow. Well, I have 4 minutes, so let's see what we can do on this problem in 4 minutes. You have a solid 3 centimeter diameter sphere of copper. So copper is a great thermal conductivity. It's a pretty high density and has a pretty good specific heat. It's in a furnace for a long time until the temperature throughout the copper is all 80 degrees C. You then abruptly remove it, expose it to 20 degrees C air, and the convection coefficient 75 watts per meter squared degree C. How long will it take for the center of the copper to be cooled to 50 degrees C? First things is, I like lumped capacitance. It's easy mathematically. I want to see if I can employ it. How do I check to see if I can employ lumped capacitance? Well, I know that my characteristic length is the radius divided by 3, and I check the Biot number to see if it's small, h L sub c over k. And when I compute the Biot number, it comes in for this problem 0.000966. What do you say? Good to go. That's what we like. All right, so now we can use the lumped capacitance. We've justified it, but you have to show this to justify it. And then you have, what's the theta initial? Well, it's starting 80, and it's eventually going to go to T infinity of 20. So what is that? 60 degrees C. We want it to cool to 50. So we're interested in the time it takes for theta to go from 60 degrees C to 30 degrees C. True? And then there's a couple different equations you can use. You can use that the time is equal to rho CV divided by HA, natural log, theta initial over theta, really just. And so we know our numbers. What's the theta initial? 60. Theta, 30. So you're going to take the natural log of 2. You're going to multiply it by rho C. I need to get the volume. Well, this is a sphere. We already showed that. 4/3 pi r cubed, and the area 4 pi r squared. Volume to area ratio, you're very observant, is r divided by 3. Isn't it? Yeah, we're done with that, but you could do it the long way as well. You have the specific heat density, the convection coefficient given. You run the number, the time comes in at 158.9 seconds. Don't give me 4 digits or more on this type of calculation, right? Good enough. Thank you for your attention.